see my screen?
We are live, Rajdeep.
Yeah, not yet. Okay, welcome to the second day, first session in this section 2. We had a special talk in the morning, so we are starting a little late. I will be chairing the session. I'm Rajdeep from TIFR. And just to let people know, the longer talks are 25 minutes plus 5 minutes of Q&A. So I'll give you a warning around 23 minutes, just to say that you have 2 more minutes to wrap up. The short talks are 13 minutes plus 2 minutes. So I'll give you a warning around 11 minutes so that you can wrap up in a couple of minutes. All questions are asked at the end of the talks. If you have a question in between, please type in the chat and we will try to take it up once the talk ends. If you have very pressing questions or arguments that are not ending, there are a bunch of breakout rooms where you can go and discuss with the speaker while the program goes on uninterrupted here. So these are the just few of the things that I wanted to remind people. And so let's get started with the academic program. The first talk of the session will be given by Professor Sankalpa Ghosh, and he will be talking from IIT Delhi, and he will be talking to us about 2 + 1 dimensional sonic black hole in a synthetically spin orbit coupled ultra cold BEC. Over to you, Sankalpa.
Yeah, so first, can you hear me? Yeah, okay.
Yes.
And you can see the slide, I hope. So first, let me start by thanking Rajdeep and others who are the organizers of this conference for this beautiful conference putting in this difficult time. And it's, more important to see each other during this particular time. And I'm very thankful that they have invited me to give this presentation. So this work is done with my PhD student, Indarpreet Kaur. She will be submitting her thesis in next 1 or 2 months. And this is the references. One published paper, one is in Steel Archive, and some couple of more may be coming. And the funding is by DAE-SRC, BRNS. You see this logo, and which is also one of the funding agencies for this particular conference also, and very helpful discussion with 2 experimentalists, Professor Jeff Steinhauer and Spielman in NIST at a different time of this particular work. So this title, as you can see, this is about the sonic black hole in ultracold BEC, particularly spin orbit coupled ultracold BEC. So black hole, of course, I just start with the initial part is very, very elementary. So the black hole is a place in space where gravity pulls so much that even light cannot get out, and the gravity is so strong, means that because matter has been squeezed into a space with a given radius, and black holes are supermassive, and this we know from the Newtonian gravitation, which essentially tells that in that region the escape velocity is greater than the velocity of light. And this is a artist picture for how a dying star get converted into a black hole, which has been taken from the NASA website. And we started becoming more educated about black hole as Einstein put forward his theory of general relativity. And so this first solution was given by Karl Schwarzschild in 1916. And this actually starts, you can tell the formal beginning of the black hole. So this quantity Rs, which is 2gm by c square, is called the Schwarzschild radius. And the surface R equal to Rs is called what is known as the event horizon. So less than R equal to Rs, so this is the region of the black hole. And it represents the point past which light can no longer escape the gravitational field. And any physical object whose radius R is less than this Rs will undergo gravitational collapse and becomes a black hole. However, the Schwarzschild black hole, or a static black hole, is a black hole that has neither electric charge nor angular momentum, and it is purely characterized by the mass which appears in this particular. And then all of you are familiar with this very famous picture. So almost after the first proposal of the black hole, almost 100 years after that, this Event Horizon Telescope has been able to, image the first clear image of the this astronomical black hole. And you can see this particular structure, which is 6.5 billion times more massive than Sun. And then came this very famous observation or the discovery by Stephen Hawking in 1975, which was built up by the earlier work of Hawking and Bekenstein, who applied classical thermodynamics to black holes. So Hawking essentially employed quantum field theory in curved space-time, and particularly near the horizon of the black hole, and pointed out that the black holes are not entirely black. They can emit thermal radiation at a given temperature. However, there are certain issues with that. First of all, the applicability of the quantum field theory at that particular point of space-time. So that has several issues with that. And second, also from a practical point of view, the temperature associated with such radiation is so low that because of the cosmic microwave background, observing such radiation even in the weakest black hole, because typically weaker is the black hole, the stronger is going to be the radiation, that is almost impossible. And there comes, so there, till now what I have told you is mostly from the general relativity and quantum gravity in a very pedagogical way, and I am neither work in neither of this particular field. So the reason we are able to poke our nose into this particular field is because of this famous, again, another very interesting discovery by William Bill Unruh in 1981, almost 7 years after Hawking's discovery. What he pointed out that, well, you should not be completely, hopeless, because you cannot never see the Hawking radiation in reality, but fluid flows can actually mimic black holes. An equation of motion of sound waves in irrotational fluid flow, which means that the curl of the velocity field of the corresponding fluid is going to be zero. That is identical to the equation of motion of a free scalar field in gravitational background. And now by arranging that background fluid flow has a region in which flow of the fluid is higher, the velocity of the fluid is higher than the velocity of sound, which means supersonic region, one can actually create the analog of a black hole. And the critical surface forming this particular analog is the analog event horizon, that these situations, and this was pointed out by Unruh in 1981 in this very famous paper. And then there is a flurry of work. So there are a lot of different systems which were targeted: trapped ions, water flow, Fermi liquid, superfluid helium, squid optical systems, and one of the most successful systems is thus far, and I will come to that issue, is the ultra-cold BEC, where some very interesting experiments took place. One can calculate the for such fluid flow the analog Hawking temperature from the analog surface gravity term, and so using this very simple formula, so you will get it all this means the details in the various papers which are cited in our work. And but the problem here is that this temperature is well below 1 Kelvin, and that makes it typically very hard to observe such analog Hawking radiation in such the fluid in such fluid system. And there comes the BEC, because ultra-cold BEC is typically observed at nano-Kelvin temperature. And a very beautiful work in 2000, Peter Zoller group in Innsbruck, they actually pointed out that it is possible to create such sonic black hole in ultra-cold BEC, and after that the work in this particular field actually started picking up. And so essentially you create a sonic horizon in such system by accelerating the condensate, by allowing it to fall to such waterfall potential created by the laser. And so what will happen that, so this is the subsonic design along the direction of the fluid flow, and this is the supersonic design. And as this cartoon picture shows, so essentially what will happen that this, if you look at this relative frame, then this fish, which is here the analogs of the sound waves, they will look like moving backward from that particular event horizon in this particular case. Okay, so the maths is very simple. Essentially, in the ultra-cold BEC, the dynamics is guided in the mean field design. It is guided by the well-known Grosspitowski equation, and you can write down this the order parameter of the condensate in this particular form, density and phase, and then you can write down the corresponding equation of the hydrodynamics. And if you look at the fluctuations around the density and the phase, you can actually find out that the effective equation is something like this, which is nothing but a Klein-Gordon field in a curved space time background. So this metric which is given in this particular equation, that mimics the corresponding matrix in the Schwarzschild black hole. And so this is the structure of this matrix, and particularly most of the studies took place in 1+1 dimension, and there the structure of this F nu mu is very simple, and it has the following form. So this is the analog metric, and you can immediately make a connection with the Schwarzschild metric in 1+1 dimension, and one can see that the speed of light will now be taken as the speed of sound, and this is the fluid velocity, which is the free fall velocity in the case of the actual black hole, and means the radial coordinate is replaced by the one-dimensional coordinate, and x equal to xc is the analog horizon for this particular system. And then came this very famous experiment by Jeff Steinhauer in Technion in 2010, and this result was first published, and he first observed the sonic black hole in the ultra cold atomic system of the rubidium atoms. So essentially he created this waterfall type of potential, and as the condensate is allowed to propagate through it, one can actually see this at this particular point the velocity of the condensate crosses the velocity of sound. However, Steinhauer figured out that there is not a one single point, but there are actually 2 points, so which looks like there are apparently the 2 horizons, and I will immediately come to that issue in the next slide. So there are issues here, of course, because Unruh's sonic analogy is actually spatial dimension dependent, and it works well because there are some issues with the one dimension, as you can look at this particular metric. So it works properly, rigorously from 2 spatial dimension onwards, whereas most of the theoretical studies and the experiment took place in 1 dimension. So the rigorous validation of the Unruh's sonic analogy does require minimally the simulation of analog black hole and analog Hawking radiation in a quasi 2+1 dimensional ultra cold BEC. And experiment and theory in this in both these higher dimensions is still very much wanted. The other issue which is very important, that almost 20 years after Unruh's discovery, Corley and Jacobson point out that because of the dispersion in this typical fluid, which not necessarily consists of phononic type of excitation, but also the other high energy excitation, what is formed is most of these cases there are 2 horizons. So one is apart from the event horizon, there is also something called an inner horizon, and the negative partner of the Hawking radiation that actually get reflected from that inner horizon, and if the system is bosonic, it actually leads to the amplification of such this superluminal part of the corresponding spectrum, and that leads to what is known as the formation of the black hole laser. So Steinhauer actually observed essentially in his experiment formation of this black hole laser and this corresponding radiation, which is called the stimulated Hawking radiation rather than the spontaneous Hawking radiation, which was originally predicted by Hawking. And then in a subsequent experiment with some experimental trick, I will not get into the detail of that, Steinhauer has been able to eliminate the second horizon and finally observe the proper, the spontaneous Hawking radiation and the entanglement between the Hawking pairs in such analog black hole in a subsequent paper in 2016. Okay, so this brings us to the issue number 2, that to realize a sonic black hole laser and the associated stimulated analog Hawking radiation, there must be at an initial time some spontaneous radiation from a sonic event horizon, and therefore in a single experiment or a single simulation you should be able to observe both of them. Is it possible to see this particular transition? So we'll try come back to this issue through our own work at a slightly later stage. Okay, now this brings us to another very important issue, and which is why that particularly the main aspect of our own work, that the massive stars whose gravitational collapse lead to the formation of the black hole, they are actually rotating stars. Thus real black holes should have angular momentum, And New Zealand mathematician Carr, he first in 1965, you can see this time difference, almost something like 50 years, half a century, first found the solutions of Einstein's equation for a situation of this kind. And such black holes are known as Carr black holes. And Carr black holes has a somewhat different structure. It has inner and outer horizon, and the region between these two horizons is what is known as the ergo region. And this has finite angular momentum, unlike the Schwarzschild black hole, which was static. And that sort of brings us to the third issue, that is it possible to observe such analog rotating black hole? And there have been very interesting work in water waves are in a photon superfluid, but the problem in both of these cases is again associated with the temperature scale, that in both of these cases observing the Hawking temperature is almost impossible. So of course one sees some singular structure, but whether this is really an analog black hole system as far as the Hawking's observation and so on and so forth, so that cannot be verified in such system. So that again brings down to us the cold atom. And there we've figured out that there is this interesting spin orbit coupled Bose-Einstein condensate. And in a very nice paper in 2017, Sandro Stringeri, he and in some subsequent paper, he actually pointed out that in such system, even the ground state contains some diffused vorticity and some finite, which he has been able to, provide the theory for that. And this possibly one of the likely system where one can sort of build a model for a rotating analog of the sonic black hole. So there comes our work. We initially took up this, shed some light on these three issues simultaneously, which I just mentioned. So we picked up this typical spin orbit coupled system, and this is the single particle atomic Hamiltonian, and it is equivalent to what is known as the two-dimensional Rajva spin orbit coupling through an unitary transformation, and this is going to be the corresponding Gauss-Pitavsky equation. So this is the model system which we have considered, and one can actually calculate the current. And if one calculate the current, one will figure out that unlike the ordinary scalar VEC, in this particular case, the curl of the velocity. So this is not an e-rotational fluid in that way. That is not equal to 0. So diffuse vorticity, even if not externally rotated. The reason why I'm talking about the externally rotated, that it is always possible to externally rotate a superfluid system and create vorticity in that, and of course that can also be treated as an analog system for such black hole. But from operational part, means creating a black hole in such rotating systems will be somewhat difficult, and that is one of the reasons why we looked at the spin orbit coupled ultra cold atoms to see the analog of these things. And then of course we did the analysis in the same way people did for the scalar VEC, and we find out that this particular analog space-time metric, here it has taken the following form. It's a two-dimensional 2 plus 1 dimensional VEC, and because of the spin orbit coupling, the velocity of the sound in the different direction, they are going to be different, and therefore this particular cloud is actually give you an anisotropic model, and that particular anisotropy is reflected in this corresponding analog space-time metric. So these are some details which involves the spin orbit coupling strength and others, and you can sort of refer to the actual paper for all these details. So we calculate, this was, so the corresponding analog space-time matrix was evaluated, and as we have, so this has been written, both in the Cartesian as well as the this plane polar coordinate, and one can actually see that there is this term, this finite velocity along the azimuthal direction, which actually makes some metric, which is in some limit identical to what is known as a very popular model for 2 plus 1 dimensional black hole, popularly known as the BTZ black hole. In some particular limit, this particular metric actually corresponds to that. And again, I'll refer to you all the details in the corresponding paper, which will tell you that, how that limit can be satisfied under a given situation. So one can plot the corresponding velocity, and one can see the finite azimuthal velocity and the corresponding distribution of the this supersonic and the subsonic design. As one can immediately see that in this system, it is not like a typical prototype black hole, which has a single event horizon, but it has an alternative region of the supersonic and the subsonic speed. So again, this is something which is associated with what is known as the formation of the sonic black hole laser. So to know more about this particular system, so this is essentially the model. So we proposed to form a typical potential here, the two-dimensional version of the waterfall potential, so that uniformly from all directions means in the two-dimensional plane, the condensate can be accelerated. Originally, this is the location of this condensate, and means as you do that, you will see this following density pattern forms. So initially there is only one event horizon, but finally there are means two event horizon, and in between that you will see there are interference pattern forms both in the radial as well as in the azimuthal directions as the system time propagates. So we use the time dependent Gauss-Pitowski equation to do this particular. So Inder did all this details work in our paper, and this is what is the typical density pattern for two different values of the spin orbit coupling strength, which you can see here. Well, so one can actually evaluate the corresponding Hawking temperature, but you have to also keep in mind that Hawking temperature, this analogy which is calculated from the surface gravity time, that is only valid when the gravitational analogy is going to be valid. And in this particular system, one such black hole laser form, gravitational analogy actually breaks down. So how to handle that? To know about more of this particular system, we essentially means need to calculate we need to extract the information about the corresponding Hawking radiation by calculating the two-point correlation function at different points of time. So this equal time correlation functions, which you have evaluated as the condensate is time propagate, and also the black hole emit particles which formed by the quantum fluctuation near its event horizon. And this quantum fluctuation in this particular model is introduced by what is known as the truncated Wigner approximation, where you essentially means populate this mode with the corresponding Bogoliubov excitations, and then you allow this particular wave function to time evolve according to the mean field Gauss-Pitowski equation. So this is essentially a combination of the mean field treatment plus some stochastic initial condition, and this thing is known as the truncated Wigner approximation. There are several very interesting literature where this particular procedure has been detailed, and it's quite popular in this particular community. So this is one of such reference. Well, so to detect the analog Hawking radiation, one need to identify regions in the quadrant that contains information about the correlation between the points with equal propagation time. So essentially, this is how you calculate the corresponding to distance, and this is the average velocity of the condensate, and this is the average velocity of the sound, and this is the propagation time. And this R prime equal to 0 correspond to the acoustic event horizon location after suitable rescaling of the coordinates, and T is the time of the emission. And as one plot this particular correlation function, one see this formation of these bands. It's very feeble here in the color, so we make the second diagram where you can see this type of bands. And these bands actually imply that there is continuous Hawking radiation. And as the system propagates further in the time, this particular continuous Hawking radiation goes away. Instead of gives this alternative pattern of the maxima and minima, which is because of the formation of the sonic black hole laser. So we have been able to clearly demonstrate the transition from the spontaneous Hawking radiation to the stimulated form of the Hawking radiation for the different values of the spin orbit couple condensate at different strength of the spin orbit coupling. Well, so that's more or less what is. So you see this. So I just provide some little bit details here. So bands are related to the Hawking partner correlations between, because you have to calculate the Hawking partner correlation from this particular expression. R prime R should satisfy this particular condition, and that is how you find out this type of bands. And you can immediately see that at a higher time, this particular set of bands actually vanish and they are replaced by the different patterns. So which shows very clearly the transition. Well, so another very important thing which turns out that one can actually calculate this expectation value of this this particular term, this Fourier transform of this two-point correlation function, and from that one can actually look at the corresponding distribution. one can immediately see that the initial time when these particular bands are present, this which corresponds to the spontaneous Hawking radiation, the distribution is something like a Planck's distribution, which is a thermal distribution. But at a higher time, this particular things is replaced by, because now there are, this interference pattern formed. So now there is a peak at a finite wave vector. So this particular thermalness of this particular distribution is now completely gone. So that actually tells that in this regime, you cannot, the same expression for the Hawking temperature, which you can calculate using the surface gravity term, that is no more valid, because the nature of the distribution is very different. And you actually, need to characterize this particular system by going beyond the corresponding gravitational energy. So that's more or less summarize what I wanted to share with you in this particular talk. So we also, put a popular version of this particular work in this Science X, which actually tells that the main finding is a very smooth transition from the spontaneous to the stimulated Hawking radiation. We are now looking at the entanglement and other properties here. So this diagram summarizes whatever I wanted to tell you, and thank you for your kind attention. So I hope I finished before the time, I think.
Yeah, you have actually managed to finish about a minute before the time, but yeah, so we have quite a few time for questions. So anyone wants to ask questions?
Yeah, I had a question. Can I go ahead?
Yeah. Go ahead, Krishnan.
Sankalpa, this is Krishnendu.
Oh,
so,
hi.
Hi, hello.
Yeah.
So one very naive question actually, because I don't really work in this field, but let me just ask this anyway. So this form of this, the sort of the metric equation that you have,
right?
Is it true that this is derived by just taking the phase only equation of motion? The density fluctuation terms is ignored there.
No. Okay. So so let me see. No. So the density fluctuation term is there. So you finally, get two equations, and then you eliminate the density fluctuation term, and so the final equation is in terms of the phase fluctuation.
Sorry, the grad square n term that you showed somewhere, is that kept or?
No. Okay. So this quantum pressure term is removed. Yes, you are right. So this particular metric is only obtainable in the hydrodynamic approximation.
Yeah. So the thing that I wanted to ask is that, with time when these density fluctuations will grow more, there must be a way when this quantum pressure would come in, right?
No, that's correct. Absolutely. So that is the whole point. So the gravitational analogy, which is entirely built up on the in the hydrodynamic regime, that actually, that breaks down when you go at the higher term, because as you have just pointed out, density fluctuation grows, and we are basically entering into the higher energy part of the corresponding Bogoliubov excitation spectrum.
Okay.
And that is the reason why you need to calculate the correlation function using the truncated Wigner approximation.
I see. Okay.
Yeah.
Thank you.
Any other questions? Sankalpa, I had one question, which is going just beyond. So if you just go one step beyond, you will get the Landau damping terms, right? So beyond just Bogoliubov approximation.
Yeah.
So do they matter, or can they be shown to be small over the time scale that you are actually?
No, I think possibly they do matter, because these are the results which you have not explored. I am sure that they do matter. Even there are also very interesting aspects like whether this stimulated Hawking radiation is very similar to the Bogoliubov-Cherenkov radiation. So there are certain issues in this particular part which is not very clearly understood. So you are absolutely right. So if you go to the next order, you will get the Landau damping term, and we have not actually considered that particular aspect. Yes.
Okay. No, just something that might be interesting to follow up.
Okay, we'll definitely talk. Yeah.
Sure. Okay. Any other questions? I do not see any other questions unless someone has a pressing question. Then let's thank Sankalpa, and then let us move on to the next talk. So Sankalpa, can you
Yeah, I stop sharing.
stop sharing?
Yeah. Yes.
And Brijesh, can you start sharing? So the next talk is by Professor Brijesh Kumar from JNU, and he will tell us about theory of a kagome-honeycomb quantum paramagnet exhibiting magnetization plateaus. So over to you, Brijesh.
Hello, thank you, Rajdeep, and good morning, everyone. You can hear me, I suppose, clearly?
Yeah, we can hear you.
Okay, good. So let me start my talk. As the chair said, it's a talk on a magnetic problem, a problem of quantum magnets. There are three keywords here. One is kagome-honeycomb lattice. The other is quantum paramagnetism, and third is magnetization plateaus. So in the remaining 20 odd minutes, what I'll try to do is take you through a story which we recently built, and we believe that we have a clear understanding of a real material. This work is done in collaboration with Magnetopa Adhikari, my student, PhD student, who is actually writing her thesis. And she is also presenting a poster on the same basically calculations which she did. So I'll skip most of the technical details in this talk, and if anybody has queries, you can talk to her, who very thoroughly did these calculations. Arno Ranko, my friend from Grenoble, who is also a part of this work, and these calculations are published in a recent PRB. So if you are interested, you can look up in details. Recently, there was a report in some papers of a quasi two-dimensional material, copper-based. This PYMCA is some organic ligand. The big name I don't have to remember for the moment. We focus on the fact that this is effectively a spin-half system forming a honeycomb lattice. More careful structural analysis by the second paper, Sugawara et al., some years ago, showed that this is not actually a perfect, I mean, it's nearly perfect honeycomb, but it still has some slight distortion by the very fact that these ligands, these organic ligands, PYMCAs, which connect these different copper blue dots through which the exchange interaction happens, they are not exactly same along these three types of bonds. And one simple way in which that distinction was noticed was purely structural, that the two bonds are nearly of the same bond length, 5.5951. And then the third one is just slightly smaller, very slightly smaller. So otherwise there is no, it's a simple honeycomb, but a slightly distorted one. What we notice that if you look at these three bonds, three types of bonds, this from the experimental paper, the cyan color, the purple color, and the yellow color, they actually form a kagome superstructure. So I'm just for convenience drawing them again and pointing out to you the underlying kagome superstructure that is formed by this distortion. Okay, so the underlying lattice is honeycomb, but what we have here is a kagome superstructure formed on it by the fact that the bonds are slightly different in lengths. And so we term this physical lattice as kagome-honeycomb lattice. So that is what I mean by kagome-honeycomb. So it's a kagome superstructure formed on honeycomb lattice. And of course, what is sitting on this lattice are spin-half, quantum spin-halves. By the way, we also noticed that these distortions, I mean, there was a recent paper by Frank and Lieb talking about possible distortions on, graphene-like systems. And this distortion is actually what they are, theorem or mathematical analysis implies. This is one of the most likely distortion. So this material is in fact a realization of it's consistent with what one expects. So okay. Another way of looking at this system is a system of coupled hexagons. As you can see, if you focus on let us say these these green black hexagons, then they are connected by red bonds. So it's a collection of hexagons coupled by red bonds. Okay, that is another way of seeing it. The important point about this material is that although it's as you can see, it's in the very basic and simple way that we understand from experiments, it's a unfrustrated kind of geometry, and yet it exhibits quantum paramagnetic behavior, which means down to very low temperatures, I think 0.6 Kelvin or something reported in the experiments by Yokotani et al. They don't see any sign of magnetic ordering. In fact, they do see signs of spin gap behavior. And furthermore, in the presence of magnetic field, they see actually the system exhibits magnetization plateaus. So there is some quantum antibody physics happening inside the system, which is not allowing it to form order, and it is not allowing it to grow the magnetization smoothly. Rather, it has these plateau-like features. So that is what caught our interest. So this is what I was saying. The specific heat, for instance, shows no signs of a thermodynamic transition, just smoothly going and looks more like exponentially suppressed. Similarly, the susceptibility is basically just going smoothly, hump and then going. Of course, this is over a larger temperature scale, but so there is no clear sign of any magnetic ordering, and there are signs of spin gapness. Then there is this magnetization plateau behavior that I mentioned to you. There is the lower and the broader plateau is at 1/3, and then there is this plateau like, these are experimental, but this little flattening that is happening around here is roughly, not roughly, but it's happening around 2/3. 2/3 and 1/3 in units of the saturation magnetization. So generally when we talk about magnetization plateaus in quantum magnets, we talk in terms of, we talk about some fractional values at which the plateaus occur in terms of saturation magnetization. Okay, so good. And also another piece of physical information, this system has Weiss temperature, Curie Weiss temperature, which is a measure of the net exchange interaction present in the system, which is about 50 Kelvin. Negative sign implies antiferromagnetic. The system is an antiferro, so it's carrying about 50 Kelvin of antiferromagnetic strength. So the interactions that are influencing or acting between these spins are of this order, roughly speaking. So as I said earlier, no geometric frustration, and yet no magnetic order, which is somewhat, so we have to understand what this non-magnetic phase, this quantum paramagnetic phase is. Quantum paramagnetic, the term for students, just basically means a paramagnetic is a paramagnetic state is a disorderly state. Generally, we associate with high temperatures with no net magnetization realized. But in many systems, even when you go down, well, ideally speaking, even to 0 temperature, then also the system is unable to order and the spins continue to fluctuate in spite of the absence or near absence of thermal fluctuations, and which only means that the fluctuations are happening by virtue of spins being quantum fluctuating. Being quantum and interacting via exchange interactions, which inherently cause them to fluctuate. So the term quantum paramagnetism. So the question is, what kind of quantum paramagnetic state does this material realize, and why are there two plateaus and so on? And in this paper, we obtained a pretty thorough understanding of these two questions and a bit more. So quickly, the basic model, as everybody has got it by now, is the basic model to look for the, to investigate for this material, to understand the properties of this material, is Heisenberg model on honeycomb lattice with these kagome distortions. So the kagome-honeycomb antiferromagnet. And because of the fact that the three bonds are slightly different from each other in their lengths, structurally speaking, so correspondingly the exchange interactions would also like to be proportionately weaker or stronger. So we allow for three different exchange interactions. Si.Sj on red bonds, green bonds, and blue bonds, and all of them are antiferromagnetic. So A, B, C all are antiferromagnetic exchange interactions. And for it's, as I emphasized earlier, and I'm again saying, it's good to think of it as a system of coupled hexagons. So you can think of AB hexagons coupled via C bonds. Okay. And just another side remark, this this geometry and this kind of material, it turned out, in the hindsight, I can say, because I worked earlier also in something similar, that this whole kagome honeycomb kind of structure was also present in a spin 1 kagome antiferromagnet. The only difference is JC, the third, let us say the link between the hexagons is ferromagnetic. So this was, there are real materials which realize this structure, but they are often, we discuss them in the context of spin 1 kagome materials, not as a spin half kagome honeycomb system. So what we have here is a purely antiferromagnetic version of that. And so the question is, what kind of physics does it have? Okay. Okay, so to describe this, just to, so we can think in terms of overall unit being 1, Ja plus Jb plus Jc equal to 1. And we can think about some limiting cases quickly for discussion. So suppose if Jc, the links between the hexagons were very strong, then of course you have independent dimers. So this phase, this material or this system can in principle be in a dimer singlet phase, because remember, we are trying to figure out which possible quantum paramagnetic phases the system may be going into at low temperatures, because that is what the material shows. The other limiting case is, imagine the links between the hexagons was 0, the blue bonds are absent. In that case, you have purely AB hexagons sitting together, but well, not interacting or nearly not interacting. So in this very other extreme limit, we have another candidate state, which is quantum paramagnetic, but more non-trivial, bigger in size. It's a hexagonal singlet state. So each hexagon would be forming locally, would be living in its singlet ground state, and as a whole, therefore, the system is also living in that hexagonal singlet phase. So these are the two limiting possibilities. And of course, the third possibility of a phase that this material may be in or not, but the material is not, but the model definitely can be in. As a theorist, we have to look for all possibilities, and that is what we are doing, is the null phase, standard up-down arrangement on this bipartite geometry. And that phase, of course, we know exists at Ja equal to Jb equal to Jc case. So this is basically just a phase diagram, ternary phase diagram, as we say, is Ja plus Jb plus Jc equal to 1. And then these three arms are like either AC hexagons being independent, or AB or PC. So any, basically they are all equivalent. Or these corners represent the other extreme limit, where you have the dimers which are being independent. So the system is in a dimer phase. Okay, so, okay, good. So let me now quickly just tell the phase diagram that we obtain using triplet analysis, which means investigating the stabilities of these two limiting phases and seeing how far in when the couplings grow, how far this phase survive in the phase diagram. And so the result of triplet analysis is basically this, which is that in the central region where J equal to JB equal to JC is 1/3 in this ternary notation, all three bonds equal, you obviously have an L phase very closely centered around that central point, the centroid of this triangle. Whereas most of the phase diagram, which is what is the notable part, that in spite of being unfrustrated system, classically this system would always have order. But here, just a small variation in ABC is sufficient to kill the magnetic order and bring the system into these the so-called hexagonal singlet phase. What we also find and of course, this is just the calculated gap versus JC. So we track this phase boundary between the hexagonal and the ordered phase by following the gap. So as long as the gap is there, the phase hexagonal singlet phase is stable phase. This is what this data shows. We also sort of find that there are very tiny regions at the interfaces between two hexagonal phases, either AB type or AC type. Let us say you can in principle have a dimer singlet phase, and it's not completely surprising because again with the benefit of hindsight, I realized that long time ago I constructed a model problem which happens to lie exactly on this line, this interface, this blue region, and there we realize a dimer phase on the kagome-honeycomb geometry. So, but the basic takeaway from this phase diagram is that the phase diagram is dominated by hexagonal singlet phase. So indeed, the small distortions are sufficient to kill the Néel order, which is generally expected on a bipartite geometry like honeycomb, and take it to a gapped non-magnetic phase, or what we call as quantum paramagnetic phase. And in principle, there are two possibilities. Dimer singlet phase, there are two obvious possibilities. If there is one third possibility, which is more complicated, but as we will see from numerics also, we don't we basically it supports that the phase diagram is dominated by hexagonal singlet phase. So this is the basic outcome of the calculation. And then we also sort of tested this finding against QMC simulations. And the QMC, so these blue circles in the middle is the data, stiffness data from the QMC simulation, because this is a bipartite geometry, so it is possible to do QMC. And we find that the agreement is not just qualitative but quantitative. So stiffness is pretty much zero outside everywhere and is significant only within this theoretically generated Néel phase. And so basically the phase diagram is dominated by a quantum paramagnetic phase, which our understanding implies is a hexagonal singlet phase. So then I can go to magnetization behavior, just look at the same model. So we understand the basic low temperature physics of this system as being dominated by hexagonal singlet phase. We apply magnetic field to this model problem and study the magnetization behavior. So what is shown here in this plot is just the level crossing diagram as a function of field of a single hexagon. And what we see that in fact, what the material is showing is a reflection of these single hexagon physics in a more normalized manner. So let us just look at the single hexagon physics first. So when the field is small, of course, this hexagon is in its singlet state, zero magnetization. When the field is increased further, it finds itself in a state which is exactly 1/3. Again, I'm plotting it for convenience as m by m saturation. And further down, you find the ground state of the hexagon having 2/3 magnetization. And finally, it saturates to being 1 or fully saturated, fully polarized ferromagnetic state. So what, and the other notable thing is the 1/3 magnetization region is broader than the 2/3, which is also what experimental data suggests, that the 2/3 plateau is much weaker, and yeah, and 1/3 is very, very clear and broad. So let us, so this is just for contrasting the two pictures, the one experimental, one single hexagon level crossing diagram. And we can do the same analysis. I mean, we did the same analysis as we did without the magnetic field. We did, effective models in these three regions, looked at their stabilities. So basically, we developed theories around 1/3 plateau, 2/3 plateau, and look for the stability of those plateaus. So that gives us the width or the regions in the phase diagram of the, and then also confirm them by the QMC calculation. So this is our same phase diagram, but now we have imposed on it through these colors and other boundaries, the information about magnetization regions. So for instance, in this phase diagram, you can call it magnetic phase diagram if you wish. What we find that first thing is that the magnetization plateaus occur only in the hexagonal singlet phase. Remember, these just remember this, these regions are hexagonal singlet phase. Okay, and the magnetization plateaus, the orange regions here, occur only strictly inside the hexagonal singlet phase, which actually is very important. So what we have theoretically proved or demonstrated, that there is, what we said, that the in the absence of magnetic field, the ground state or the low temperature phase is a hexagonal singlet phase. And the fact that the system exhibits these two plateaus demonstrate or implies that the ground state must be hexagonal singlet. Okay, so if it were not in hexagonal singlet phase, you would not find these plateaus. So it's a reverse implication, if you wish. Then what you find further, that the 1/3 plateau is always it occurs for larger region of the phase diagram. So 2/3 plateau is always going to be sort of smaller, and which means system may or may not have 2/3 plateau, but it will have 1/3 plateau as long as its ground state is hexagonal singlet. And we, as I said, we checked these against numerical simulations, and and we find them to be basically correct. So our theoretical understanding agrees with unbiased numerics. So what we have is basically what we obtained from our theoretical understanding: two plateaus, the possibilities which material exhibits actually, or in only one plateau at 1/3, or no plateaus at all. And magnetizing plateaus occur only in the hexagonal singlet phase. And in fact, we also estimated the position of this material in the phase diagram. And so you see these little black, lines here. This is roughly the window or the place where the material JA, JB, JCs must belong. Okay, and because 2/3 plateau is very small, we expected it to lie close to the purple boundary, which is the boundary of the 2/3 plateau. So purple line is the boundary of that region where both 1/3 and 2/3 plateaus occur. And this material indeed unsurprisingly lies, from our estimate with the experimental data, it lies very close to the purple boundary. So we actually requested the experimental group to share their data with us, and so the blue line is experimental data, and dash line is the estimates. So we basically did a guided search of JA, JB, JC using our Triplon analysis, and then generating for suitable parameters the numerically exact data, and comparing with the experiment, and we find this to be the best basically choice. So the scale, as you can see, is comparable. Remember, 49 was the overall Curie-wise scale, and we are pretty much there. And so this is basically what we have.
Brajesh, just to remind you, maybe
Yeah.
you can
Yeah.
wrap up in a couple of minutes.
Yes,
Yeah.
yes. That's right. Yeah, it's almost done. Just maybe
Okay.
one more slide. So what we can see,
well.
so what we see here is clearly that JA, JB, JC, JA and JB are comparable. In fact, they are exactly same apart from this small. As you can see, JA can be slightly bigger and JB could be slightly smaller. But the third coupling is always significantly smaller. And hence, now there is a very consistent picture that we have. Hence, it has to be in a hexagonal singlet state. So the fact that there are two plateaus already fixes it to be in the hexagonal phase as per our theoretical understanding. And then these estimated couplings further clear that picture. So yeah, so these black lines are basically in some dimensionless units where so these are of course dimension full numbers, but if you convert them to suitable dimensionless numbers, then they belong here, these three little black points. One interesting thing to remark finally before I close is that this estimate puts this material very close to a quantum phase boundary. This phase, the purple line, which is the boundary between having two-third plateau or not having two-third plateau. And something happened. Why did it freeze?
Maybe you want to stop sharing and resharing if it has frozen.
It just suddenly froze. You can hear me though, right? But I don't see.
We can hear you.
Now okay, it's coming back. Okay, good.
Yeah.
So it leads us to make a testable prediction actually, and which is that while by applying some strain or some pressure, even a mild one, because remember the material is very close to this two-third being there or not there kind of phase boundary. So one can actually make this two-third plateau disappear systematically, and thereby, so this is basically a testable prediction for experimentalists to look out for. So let me conclude by summarizing. This compound Cu2 PYMCA3ClO4 is a kagome-honeycomb quantum paramagnet because the superstructure is kagome on top of honeycomb. Second important point, it realizes hexagonal singlet phase. So this is an example. Remember this long history of quantum paramagnets, dimer phases, and then maybe square placket phases. So in some sense, this is going further in that sequence of realizing quantum paramagnetic phases with bigger plackets. And in this material, we have an example now. We are clearly sort of demonstrated that we have a case of a hexagonal singlets, which means these hexagons independently or quasi-independently form singlets and live together in the ground state. And as I said, the existence of one-third plateau is already a proof of that fact.
Brijesh, can you wrap up a little?
Yes, it's
quickly?
done. And the material lies close to two-third boundary of plateau region. And in principle, one can, make it undergo a quantum phase transition by applying pressure or strain. Thank you very much.
Okay. Thanks, Brijesh. Questions from the audience? We have about a minute or so for the questions. Yes, Yogendra.
So
go ahead, ask your question.
I have a general question.
Yes, please.
So to expect magnetization plateaus in the system, is it necessary to have total magnetization to be a conserved quantity? And so what are the signatures of these magnetization plateaus in the transport or any susceptibilities?
Well, okay. Firstly, it is by transport. If you mean the electronic transport, this is an insulating system. And of course, magnetization plateaus are magnetization plateaus. You see them in magnetization, so you don't have to see anywhere else. I mean, it may have indirect influences somewhere else, but the answer to your first question that what do you need? Well, you need a gap for a plateau to occur. Plateau means so magnetization. So you apply magnetic fields in small steps and you measure magnetization. But a plateau is a place where the magnetization stops increasing, even though you are increasing the field, which means the system is now finding it convenient to stay in a state and not go to the next state where magnetization is slightly bigger. So magnetization plateau, occurrence of magnetization plateau is essentially saying that the system has gone into a state where it is no more favorable to increase the magnetization, but to, and that is protected by a gap. So for example, if I go back to this this single hexagon figure here, what it is saying, initially it was in zero magnetization plateau state, which was protected by gap, which is what the hexagonal singlet phase is. Then it gets it is finding itself convenient to stay in the next state, which is which means the local at the level of hexagon, the ground state is a triplet, not a singlet. And again, it is protected by gap to both singlet state and to quintet state. And the next state is a system find itself convenient energetically to stay in the quintet state. So it gets stuck in quintet state and again protected by gap to a singlet and to a neighboring triplet or a haptet. So the existence of plateau basically is ensured when a particular magnetization state is protected by gap to its neighboring states. Yeah, I think that is possibly the best answer I can give if I understand your question correctly.
Okay, thank you. Maybe just one question from Mayuk, and then we will move on because we are pretty fast.
Yes.
Thank you, Professor Kumar, for the nice talk. So just one question. So is there any possibility to have key-type exchange interaction in your system?
Well, this material doesn't have key-type interaction, yes, but in principle, there is a possibility and to study key-type kind of interactions on this geometry. And this is something we are actually in the process of doing. So that is, yeah, that's a good sort of anticipation. Thank you.
Yeah, just one more, if Professor Senshanma allows, just a quick one.
Go ahead.
Okay. So yeah, so I mean, you have also, I mean, of course, you have found out the exchanges and everything. So you have in the low temperature, you have some gapped behavior in the susceptibility, as probably it should be. Because you have,
and specific heat and so on. Yes.
Yeah. So can you also estimate the gap value from your theory as well?
Yeah. Gap value we can estimate. Yes.
Okay. And
it is given in
with the experiment.
Well, it's in the same scale. Yes.
Okay. Thank you.
Same scale.
Okay. Let's thank Brijesh for a very nice talk. We are about 3 minutes over time. So
thank you very much.
Brijesh, can you unshare and then so that we can go on to the next talk. Hridis, would you share? Okay, so the next talk will be given by, what happened to Hridis?
Yeah, just a moment. I think it went away. Okay, can you see me? See my slides?
Yes. Okay, so the next talk will be given by Professor Hridis Pal from IIT Bombay, and he'll be talking to us about quantum magnetotransport in the semi-classical regime and negative longitudinal magnetoresistance. So over to you, Hridis.
Okay, thank you, Rajdeep. And can you all hear me well and see my slides?
Yeah, go ahead. Yeah.
Okay, thank you. Yeah, thanks a lot for inviting me to give this talk. And before beginning, given the unusual circumstances, I hope everyone is doing well and they and their family are all in good health. Hopefully we'll get over this soon. Okay. All right. So today, what I'm going to talk about is my recent work on magnetotransport, in particular longitudinal magnetoresistance. And I'm going to tell you about a story that I've developed that may have been missed in spite of this topic being a really old topic. So here is a quick outline. So I'll start with a brief introduction to what essentially people mean when they talk about magnetotransport. In particular, the various regimes that one focuses in this field, and then in particular what longitudinal magnetoresistance means, LMR, and what the current understanding is of this phenomenon. And then I will go on to the next part, which is there is probably a new contribution in weak fields, which has not been accounted for before. And this gives rise to some very interesting consequences. For example, it will give rise to negative longitudinal magnetoresistance, which is prohibited by classical theories. And I'll show you that the origin is essentially quantum, even though we are in a classical regime. And then finally, I'll summarize and briefly state some of the possibilities. Okay, so let's start. It's a very simple idea. If I have an electron in a magnetic field, well, if the electron is moving and giving rise to some current, I know that if I apply a magnetic field because of my simple Lorentz force, I will get a force which will try to curve its path, right? That's what our essential high school physics tells us. Now, if we are looking at this problem from a classical point of view, then we know that these closed paths can be of any radius. So essentially the energy and the path, both in real space and in reciprocal space, whichever way you want to think, these are continuous. It can take any form. When one moves to the quantum description, the basic phenomenon stays the same, except that these paths are now quantized. Okay, so not all paths are allowed, not all circles are allowed, either in reciprocal space or in real space. And these are the so-called Landau levels. So if I think about from the energy perspective, let's say I have a simple parabolic spectrum. I know that these the energy gets quantized into Landau levels, and they fill up to the Fermi level, because let's say we have a metal, and the typical spacing between the Landau levels is given by the cyclotron frequency, which is proportional to the magnetic field, meaning as I increase the field, the spacing increases. Okay, so without even going into any kind of calculation, let's sort of give us have a look at a typical dependence of the resistivity on the field. So here I'm talking about the diagonal part, so the resistance, not the Hall part. So if I just think about simple resistance, which arises in any material, and now have applied a field, essentially then, given the picture I showed you in the last slide, you can think of it in the quantum regime or in the semi-classical regime. Now, what differentiates between the two? Well, I've told you that in the quantum sense, once you apply the field, we have discrete Landau levels, right? And so for a given field, there is a certain number of quantum Landau levels which reside inside the Fermi level. Now, in the extreme quantum limit, which is when this omega c, the spacing becomes of the order of the Fermi energy, essentially you just have only the last Landau level populated. And this is where you have the extreme quantum regime, right? On the other hand, if you go to a regime where there are lots of Landau levels under the Fermi level, so let's say capital N, which is much, much greater than 1, then this is essentially our semi-classical level. Yeah, and this regime then will have a different behavior with the magnetic field in terms of resistivity. Now, even though this is one particular regime, there are two different aspects that get in. Okay, so let's start with the extreme small field. Now, at this point, the spacing between the Landau levels is so weak and so feeble that essentially you can just treat this as a classical object. There it is. This is as a continuous distribution of the density of states, and the only effect of the magnetic field is just to curve the path. So we can think of just the Lorentz force and be done with it. However, if I increase the field, but I'm still inside the semi-classical regime, meaning n is much larger than 1 number of Landau levels, a vestigial signature of the quantum effect will kick in, because you see every time I change the field, the spacing increases and one Landau level will pop out of the Fermi level. And because of this discrete change in the density of states, you will start have sudden changes in the resistivity. And that is what is essentially termed as quantum oscillations or Shubnikov-de Haas effect. Now, in this talk, I am going to be concerned purely in this regime where the classical kinetics plays a role. That is, the n is really much larger than 1, and we just think of the Lorentz force, forgetting about the discrete nature, right? Okay, good. So let's now concentrate on this regime and let's think about magnetotransport. So let's say I have a 3D material and I apply my field in the z direction. As usual, because of the field, my electrons curve. And the effect that one has on the classical resistance can be thought of in two ways, depending on the mutual directions of the field and the current. So it is called transverse when the field and the current are perpendicular. And in this configuration, of course, we expect the Lorentz force because velocity and b are perpendicular. So they will curve, and eventually it will give some resistance, let's say rho with b. Okay. Now, the important thing to remember here is that essentially this will be positive, and you can prove this by writing the kinetic theory. And you can also understand without doing any calculation. Why? Because you see what is happening is, let's say the electron going from this point to this point in the absence of magnetic field will encounter certain impurities. But as you apply the field, the path will curve, meaning it will travel a larger distance. And if the impurity is homogeneous, then it will just get more restrictions from the impurities. As a result, the resistivity increases, and that's why this is a typical curve. Okay. And the other thing to notice is that this dependence of the field enters through the quantity omega c tau, because again, these are the only two scales available, right? Omega c encodes the field. And because this is coming from the extended path, that is the sort of time scale mean free path that enters into the calculation. And this is the dimensionless quantity with which things will scale. Let's now focus to the other geometry where the current and the field are parallel. Now, in this configuration, of course, there is no Lorentz force, which means that you would expect that the resistivity should have no dependence on the field and LMR should be 0. This is what one expects classically. But does that mean that LMR is 0? In fact, if you ask any experimentalist who works on transport, you'll realize that it is actually quintessential. I mean, almost all objects show you non-zero LMR. Now, it turns out that within this same basic mechanism, kinetic theory, your LMR can still be non-zero. And there are basically two ways by which you can achieve that. The first is if your dispersion is anisotropic. And not just all kind of anisotropy, the anisotropy has to be in a very special way. And what is that special way? The dispersion has to be non-separable in the direction parallel and perpendicular to the field. And you can intuitively understand why this will happen, because as the system is getting dragged parallel to the field in the current direction, it is inherently coupled in the perpendicular direction because of the dispersion itself and picks up a component. And that's how you can get some contribution to LMR. And this can be shown just by doing a simple kinetic Boltzmann equation, which we showed back in during my PhD. Okay, and again, you can show identically that if it so happens, it has to be positive. There is another way which has become very fashionable and very popular of late, which is if the dispersion has a topological character, right? So this is, for example, a wild semi-metal where we know that the LMR is a telltale signature of such kind of systems. And this happens because you don't need any anisotropy, but it still gives you a contribution because it is not just the Lorentz force which contributes, but there is an additional force from the Berry curvature, which I'm calling within quotes Berry force. And because of that extra force which acts in the direction of the field, you just get a contribution. But the interesting thing is that this is necessarily negative. Okay, there are other ways of also getting non-zero, but this is beyond the scheme that I'm interested in. Either it is beyond semi-classical, for example, ultra quantum or weak localization, and so on and so forth, or you need to have tailored models of scattering, which is an extrinsic way. I mean, not any disorder, but very specialized models which can give you non-zero LMR. Okay, good. So with that background, now let me dive into the main idea, which is, can there be a new contribution to LMR? So I have shown you that within the kinetic theory, within in the weak field regime, there are these two ways essentially known to us. What I'm going to propose is that there is a third way which arises and can give you non-zero LMR. And this is due to the change of density of states due to the magnetic field. And this has a very interesting, two interesting consequences. I'll show you that this is non-zero for any dispersion, even parabolic, which goes against this. And it can be negative even for a non-topological dispersion, which is contrary to this. So what is the essential idea? To appreciate the idea before getting into any calculation, you can immediately understand where this is coming from. And to appreciate that, let's just consider another physical observable, our good old Landau diamagnetism. Okay, this is the orbital magnetic susceptibility that we calculate in our textbook. Now, what is the origin of Landau diamagnetism? We all know that classically, for a free electron system, there is no diamagnetism. There is no magnetic susceptibility. Because why? A magnetic field cannot change the total energy, right? However, as Landau showed back in 1930s, quantum mechanically it is non-zero. And this is because once you go to quantum mechanics, there is a discrete Landau level formation, which does change the total energy. Now you see, this is a quantum effect. However, by definition, susceptibility is a small field effect. You go to the limit where field is zero. So this is a low field phenomenon. So I'm essentially going to borrow this idea for conductivity. So if I think of just the standard Drude model, n squared tau over m, I can just think that leaving everything else, this total density, which is constant in my classical regime within the kinetic mechanism, should also inherit some kind of dependence on B because of this dependence of the density on field because of the quantum nature, right? And that, even at low fields, just like my magnetic susceptibility, should give me an effect in the conductivity. Now you see, this is a generalized idea. It doesn't matter what the configuration of the field and the current is, which means I expect it both for transverse as well as longitudinal. However, because in transverse, there is always the kinetic part, which gives you a large contribution. This will always be subleading and you can neglect it. But as I've showed you, for the longitudinal part, unless the dispersion is very specific, your LMR kinetic effect can identically be zero, which means this can actually turn out to be the leading contribution. Okay, so if you're convinced with that argument, let's now just dive into the calculation. To do the calculation, I'm just considering a spectrum, a general spectrum, but separable in the two directions. Z is the direction of the magnetic field and XY is perpendicular. Now, I don't need to do this. I can do it in all generality, but I'm choosing this for two reasons. One, simply because the calculation is somewhat easier. But more importantly, this is a spectrum that I know kinetically will give me zero. Why? Because the motion perpendicular and parallel to B are decoupled by construction, and this is not topological by assumption. That means if doing my exact calculation, if I get any contribution to LMR, I'm absolutely certain that this is a new effect, which cannot come from kinetics, okay? All right, so the method is very standard. Given this general spectrum, I can calculate the Green's function, single particle Green's function in the presence of the field. The phi's are the generalized Landau levels corresponding to whatever spectrum it is. I don't need to know the exact form, but I can use this and apply the Kubo formula. And after a little bit of manipulation, you can simplify to get the following form for your magnetoresistance in the direction of field. Now, this has a very intuitive meaning. What does it mean? Well, VZN is nothing but the velocity in the Z direction corresponding to Landau level N, okay? Now, what does this mean? Well, what has happened is my 3D spectrum, as we all know, has broken up into Landau levels, which are dispersing in one direction. So these are essential one-dimensional dispersing dispersions, energy spectrum. And because these are Landau levels, this B in front is telling us how degenerate they are. So each level is highly degenerate with the field. So all I have to do now is I have to just take, as in any one-dimensional model, there is a Fermi level. I just take the velocities at each point that the Fermi level crosses in these one-dimensional levels, add them up, and I should get the conductivity, right? Okay, good. So as a warm-up, let's try it with a parabolic spectrum. So we know the parabolic spectrum. We know the dispersion in the Landau level dispersion in presence of the field, n plus half. We can easily calculate my VZN that I need here. Yeah, that's very easy to do. And I plug it in. Okay, so now I have to do a discrete sum over all Landau levels up to the Fermi level. So you see 1, 2, 3, 4, 5. And as I change the field, of course, this number changes according to the function of the field, and that I have to incorporate. Now, that's not very hard to do. You can easily change these discrete Landau levels into an integral by using the Euler-Maclaurin formula. And because I'm interested in the low field regime, I truncate it at order B squared. And lo and behold, once you do that, you do see that the sigma ZZ is not just the Drude part, but there is indeed a correction that scales quadratically with the field, which is essentially my non-zero longitudinal magnetoresistance. Okay, so here sigma ZZ0 is the root part, where N0 is the zero field density. Okay. Now, one thing to notice here is that you see in the correction there is no tau here. It is purely scaling as omega c over EF, which tells us that this is not a kinetic contribution, because otherwise it would have scaled with omega c tau. This is really a quantum contribution, even though I have gone to the classical regime in the limit of b going to 0. Okay. Now here, of course, once I invert this, the resistivity will get a plus sign here, meaning the contribution here is positive. Good. So with that little exercise, I want to now generalize to an arbitrary spectrum. Now, in order to do that, of course, for any arbitrary spectrum, I don't know a priori what the Landau level spectrum is. So I'm going to use the semi-classical quantization condition, where this S here is essentially the area of an isoenergy contour in K space perpendicular to the field. Okay. So for example, if this were a parabolic spectrum, it's just a circle as a function of K and energy. And here gamma is the semi-classical phase, which, for example, in a parabolic spectrum, we know it's half. So if you, for example, put area of a circle here as a function of energy, you'll immediately get E as a function of E is n plus half omega c. Okay, but this is the general form. Now, when I move from parabolic to a general spectrum, what will change? Well, the first thing to change will, of course, be the area, because for an arbitrary spectrum, the cross section of the Fermi surface is no longer going to be a circle, but that is easy to incorporate. You can just do it geometrically. What is more crucial and more interesting, and is really behind what I'm going to tell later, is this semi-classical phase gamma. It turns out that this gamma equals half is not a constant, but it is really true only for a parabolic spectrum. In general, this gamma, like the S, is also a function of energy. And this was done, in fact, long back in the 60s by Roth and Landau-Peierls. Essentially, you can think of gamma as a function of energy, which can be related to its zero field quantities in the following way. Okay. On the other hand, so this is what Roth showed how to get gamma. So you can see there is a correction on top of half. On the other hand, Landau-Peierls' formula for magnetic susceptibility tells us that chi of at any given energy E can be written in the same form. And if you just compare notes for the two expressions, you can easily write this concisely, relating this semi-classical phase gamma to the orbital magnetic susceptibility. Okay, so that's a very concise way of writing this formula. So I go back to my same initial Kubo formula expression. Now I find Vz from this expression using the fact that S and gamma are now functions of E. And essentially, it's the same method. I go through Euler-Maclaurin truncate at order B square. It's a little cumbersome, but once you go through the algebra, you get the following expression for your longitudinal magnetoresistance, where sigma ZZB is sigma, the zero field part, and then you have a correction which scales as B squared. Note here, the tau here, it does not mean that this is scaling with tau. This tau can be absorbed in the root part, meaning the correction itself is completely independent of tau. Okay. And then once I invert the conductivity, I get the resistivity as the root part plus alpha B squared, where alpha is this entire contribution in the, the expression in the third bracket. Good. So I have the following expression, and you can easily see that this will reduce to the parabolic thing once you include the parabolic spectrum. But what is more interesting now is that you see for a non-parabolic spectrum, for a general spectrum, alpha now has contributions from two terms. And these two terms need not be of the same sign. And I can demonstrate that to you by just considering the following. Let's say that I keep my parabolic spectrum in the Z direction. Don't change that, and just change the XY part perpendicular to the field as a square lattice spectrum. Okay, that's my easy way to introduce non-parabolicity. Now for this spectrum, the 2D orbital magnetic susceptibility is very easy to calculate. This is known. Okay, and I can calculate the velocity here, which is essentially just inverting this and including this here. So E is EXY. And then I can plug it in here and just calculate. And here I'm plotting for you alpha as a function of the filling. Now you see when the filling is very low, that means this part is almost parabolic, this part is almost parabolic, I get alpha, which is positive, which is what I had calculated earlier. But as I increase my filling, which is given by this Fermi energy, of course, the non-parabolicity is kicking in here. And as you see that at a certain amount of non-parabolicity, here, alpha actually switches sign and just goes to the other side. It tells you that for a simple spectrum, my longitudinal magnetoresistance actually changes sign, and it does become negative as non-parabolicity becomes pronounced. So the solid curve is according to this expression. Ignore the dots, they will become relevant in the next slide. Okay, so now that I've showed you the analytical expression, it's good to also numerically verify it. So it's not very difficult because this is simple square lattice. I took a lattice model for this, and then you can actually calculate the Landau level spectrum exactly. It's like a Hofstadter spectrum. You do that, you plug it into your expression for conductivity, and this is what you get. So this is my sigma ZZ as a function of the flux. Flux is a placeholder for the field, flux per placket, I mean. And as you see, for low filling, sigma decreases with field, meaning resistivity increases positive. And as you go higher and higher in the filling, sigma increases with field, meaning the resistivity decreases. And I can fit this to quadratic forms, and I extract the coefficient of the quadratic part. And this is exactly what the dots are. And you can see there's an excellent matching between the analytically predicted form and that which I derive from the numerics. Okay. All right. Rajdeep, how much time do I have?
Yeah, you are almost maybe a couple of minutes.
Okay, good. I'll round it up. This is my last slide,
Yeah.
so I'll just rush through.
Yeah, sure.
Just one last point that I would like to make, and this is sort of something that one could ask is, so what I'm claiming is very simple. At the end of the day, I'm just playing with this n and saying that this is proportional to the density of state, right? And this is where all the change is coming from. And throughout the calculation, I kept my tau to be a phenomenological constant. But someone can challenge and say that, look, in an actual microscopic theory, it is 1 over tau, which is also proportional to the density of state, which means tau itself is 1 over density of state. And is it possible that the effects can just cancel out? Yeah. So for that, you can easily check. So this was the expression I showed for constant tau. And now, of course, to have a tau, I have to adopt a model. I cannot be general anymore. So I use the simplest model of weak dilute delta impurities, and I go to first born approximation. And you can show that this is the expression. And now you see that once you plug this into this expression, along with this, it's clear that they will not cancel anymore because the summations, summation of VZ and summation over 1 over VZ, they are completely different. There is in fact no cancellation. And if you take a model spectrum as well, which you can do, I'm not showing you the calculation, and do both simultaneously and calculate, you see that it does survive. In fact, it actually accentuates the LMR. Okay, good. So that's all that I had to say. So I'll summarize. So what I've tried to show in this presentation is that in addition to the popular kinetic mechanism that works in the classical regime, LMR can also arise due to the dependence of the density of state on the magnetic field. And there are two interesting consequences of that. The first is, unlike the prediction of the conventional wisdom, in fact, all dispersions inherently show LMR. Okay. And the second interesting aspect is that if the dispersion is non-parabolic, it doesn't matter if it is not topological, it can show negative LMR. And this is important in the context of using negative LMR as a sort of a telltale sign of these topological semimetals signature. Okay, and the second interesting aspect is that the origin is entirely quantum here, but it is manifesting in a classical regime of weak fields. Okay, going ahead, what can be done? Of course, the idea in this calculation, I considered the simplest possible case, which is a non-topological isolated band. But of course, you can now include the same mechanism and extend it to topological systems, and I expect novel behavior to emerge there as well. And I'm currently working on that. Okay, hopefully I'll get some results soon. Okay, thank you very much for your attention. If you're interested in further understanding, you can look at this reference, and I would like to acknowledge support from IIT Bombay in the form of seed grant. Thank you.
Thank you, Hridis. Questions from the audience?
Rajdeep, can I ask something?
Yeah, Vikram, go ahead.
Hridis, I liked your talk. I have a question related to your interpretation. So you said that this is a density of states effects primarily. And so on the square lattice, you showed us different Fermi levels and how for each of them you could have different kinds of magnetoresistance. So does this negative magnetoresistance have anything to do with the Van Hove singularities and the Fermi level lying in its vicinity or not?
Not yet, no. Not
so
yet.
These are very much below that?
Yes, it's very much, so I mean, the fillings that I've considered here are all far from Van Hove singularities.
Okay, and anything weird happens at that point because you have a divergent density of states?
It should, precisely. That is precisely the point that I'm working. See, the point is, I mean, since you mentioned this, I can already show you. You see, this contribution is going as, the interesting part is coming from the derivative of the magnetic susceptibility, right? And susceptibility itself should also have a density of state in some sense. Not should, it has. So anywhere this susceptibility, if there is a divergence, you see, even to order B squared, I cannot truncate this. It will have a large effect. And I do expect these things to be interesting. First, in what you mentioned, which is near a Van Hove singularity, and also in a Dirac system where we know, for example, in a simple 2D Dirac system, the susceptibility diverges at the Dirac point. And that's essentially where I'm getting at next. Does it make sense, Vikram? Did I answer your question?
Yeah.
Yeah, thank you.
Any other questions? So, if not, so Hridis, I had one question for you. So, you are trying to get the non-parabolic band effects, but you are also trying to stay away from the Hofstadter regime, right? Because, so, is it one way to say this as the first corrections which will ultimately lead to the Hofstadter regime? So you are saying that you can still stay away from that?
Yeah, absolutely. So,
I mean, leading order corrections, you build it up and you get to the Hofstadter regime. I see.
Yeah, exactly. I mean, this is not just away from Hofstadter. This is far away. So yeah, if you just take this, the Hofstadter is somewhere here. This is not only far from there, it's even far from the quantum oscillation.
Right.
So it's really
okay.
Yeah.
Okay, so let us thank Hridis for a very nice talk, and let's move forward. So Hridis, thank you very much. Can you share your slides? And Manoranjan, can you share your slide? Yeah, so the next talk will be given by Professor Manoranjan Kumar from SNBOSE Center, and he will be telling us about quantum phases of ferromagnetically coupled dimers on the Shastry-Sutherland lattice. So over to you, Manoranjan.
Okay. Thank you, Rajdeep. Thank you very much, and good morning, everyone. I'll start my talk thanking the organizers for giving me opportunity to present this work. So today I'm going to talk about the quantum phases of ferromagnetic coupled dimers on Shastry-Sutherland lattice. These two collaborators have contributed most of the work in this talk. So here is the plan of my talk. So I'll be first talking about the Heisenberg model on Shastry-Sutherland lattice. Then I'll give a brief review of the recent results. And I'll be also talking about the quantum phases and their characterizations. And then I'll present the quantum phase diagram, which is calculated from the DMRG method. At the end, I'm going to talk about the non-collinear phases and the pitch angle and their dependence on the parameters. Okay, so here is the lattice, the Shastry-Sutherland lattice. And you see here, it looks like a square lattice, but only thing difference you have here is every alternate squares have the diagonal bonds. So this blue color diagonal bonds I'm talking about. And it's a very interesting that if you have this blue bond, which I'm showing, if it is antiferromagnetic in nature, irrespective of what is the nature of the exchange interaction along the squares, it is going to be frustrated. Okay, and like today's talk, I'll be focusing on mostly when your exchange interaction along Jx and Jy are ferromagnet and the diagonal bonds are antiferromagnet. Okay, so how to write how the Hamiltonian will look like? If I write the Heisenberg model on a Shastry-Sutherland lattice, so this is the first term, which is representing the exchange interaction along the x-axis, this green bond. And the second term represents all the nearest neighbor bonds along the, which is represented in the red color. And this diagonal bonds are represented by the blue curves. So this is antiferromagnetic in nature, and Jx and Jy are ferromagnetic in nature. Okay, so let's go to the most recent studies on these models, especially on the Shastry-Sutherland lattice. I'll be considering when only those studies first where all three interactions, Jx, Jy, and J diagonal, are all antiferromagnetic, and this model is very well studied. I'll be giving only few references here, although there are lots of studies. So most recent one are these Carbos and Millers, and they have considered this model considering Jx and Jy equal, and they assume this is J, and the diagonal exchange is antiferromagnetic, even that Jx, Jy is also antiferromagnetic. The diagonal exchange is set to 1, and they use the IPEPs to solve this model. And what they observe is that in very small values of J, you have a dimer bonds are dominant. Therefore, okay, just a minute. Sorry, I don't know why it is not coming. Sorry, let me go with this one only. So if your J1 is small, your diagonal bonds are dominant. Therefore, the dimer phase stabilize, and these dimers are along the diagonal bonds. And in strong J limit, your exchange interaction along the squares are dominant. Therefore, the nail phase is going to be stabilized. And there is a very small parameter regime where the plateau phase gets stabilized. And this just lies between 0.65 and 0.75. Whereas the another study by Lee et al., they considered the same model, and their interaction, only the parameter has been redefined here. Jx and Jy is equal to J1, and the diagonal bond is represented as J2. If you see the phase diagram here, what they observe, that they find that at very low values of J1 by J2 ratio, your ground state have dimer valence bond solid, whereas at large value of this parameter, you have nail phase. And in the mid regime, you have plaquette valence bond solid. Okay, and they also observe the deconfined quantum critical point. Okay, so this is all theoretical, but recently this paper, Jayad et al., they observed many phases experimentally, and they used the inelastic neutron scattering, and they saw that these phases indeed exist in experiment in the real material as well. Okay, so let's go to some materials, new materials, I would say, although it is 10 years old, but for us it is still new because it's not properly modeled yet. What I'm showing here is the copper oxyhalides, where the two magnetic layers, these are the magnetic layers here, and this is these two layers are separated by these non-magnetic layers. So effectively, your magnetic interactions are confined within the layer. So it's a two-dimensional system. If you see here, I'm representing this just copper and chlorine atoms here, and it's in 2D AB plane. And what you see here that you have various kind of exchange interactions. And what they found that the nearest neighbor bond are weak compared to the next nearest neighbors. And this nearest neighbor is ferromagnetic in nature. And this paper, actually, Tassel et al., what they did is they have the experiment and also some of the DFT calculations supporting the idea. And what they found that you have three dominant interactions. J1 and J2A are ferromagnetic in nature, which are nearest neighbor bond, which you can see the blue line and this bond. And the red bond represents the next nearest neighbor or the diagonal bonds. And that have, if you consider the diagonal bond as 1, the ratios of the other two are around -0.4. Okay, so you see here that you have a square-like structure, and then next nearest neighbor are diagonal like structure. And then Furukawa et al., they try to model this material using their DFT parameters as well as their information. And you can see here the blue and the red lines are nearest neighbor interaction, and this again diagonal bonds are your antiferromagnetic interactions. And if you rearrange this, it looks like exactly like this, which you can recognize this is nothing but Shastry-Sutherland lattice. And what they consider is the nearest neighbor bonds, which are represented as blue and the red line. And it's a ferromagnetic in nature, whereas the next nearest neighbor, so when I say next nearest neighbor, this black bond, are antiferromagnetic in nature. And as I have written earlier, the model Hamiltonian can be written like this. Okay, so they try to solve this the model Hamiltonian using two methods. It's exact diagonalization method and Schwinger boson mean field theory. And they're all the calculation, ED calculation, are restricted to 24 site calculations. And here is the phase diagram. You see that they have many phases. So our calculations we are interested only in the regime where the Jx and Jy are ferromagnetic in nature. And they found that there is a ferromagnetic phase, this phase, in large J1, Jx and Jy limit, whereas the stripe phases, like there are two types of stripe phases exist. One is 0 pi and other is pi 0. They also observe dimer singlet phase, and there are three types of dimer singlet phase they observe, but they don't characterize based on the ground state properties. Rather, they characterize these phases based on the magnetization curve. So I'll not go into that, and I'll completely avoid that. And they don't find any spiral phase. I think because of the size limitations, they have a very small cluster they can't get this like a spiral phase calculated. Okay, so they also did the Swinger boson mean field theory, and they get 6 interesting quantum phases. There are 2 types of stripe phases. It's a 0 pi and pi 0. 2 types of spiral phases. Okay, it's one is along x direction, other is along the y direction. There is a 5th phase is the ferromagnetic, and 6th is dimer singlet phase. And you see here that their dimer singlet phase is dominant even at very low values of like a jx and jy. And this diagonal bond is again the perfect dimer singlet phase. What they find is the perfect dimer singlet phase, which is jx is equal to j1. They separate the x spiral and y spiral. And okay, so what we find is this is very different from the exact diagonal calculation. Although these phases, the spiral phase was not there, that stripe has, again, the phase boundaries are different here. Okay, so before going to the DMRG calculation, let me tell you the quantum phases and their characteristics. Here I'm showing you all 6 phases, how the arrangement of their spins will look like. When I say this stripe phase 0 pi, I'm saying that along the x direction, you have a ferromagnetic arrangement of the spin. You see here, it's all up. Whereas along the y direction, you have anti-ferromagnetic arrangement. Similarly, that if it is a stripe pi 0, that means along the x-axis, you have anti-ferromagnetic alignment, whereas along the y-axis, you have a ferromagnetic alignment. For x spiral, you have the spiral variation. So you see that it's like a rotating along the x direction, whereas along the y direction, you have the all ferromagnetic arrangement. Okay, so when similarly, if you have y spiral, you have like the rotation, the spiral behavior along the y-axis, whereas along x-axis, you have a ferromagnetic arrangement. In perfect dimer phase, all the diagonal bonds are dominant. And if you try to see the bond order along any other direction, it will be all 0 except this diagonal bonds. So basically, I'm trying to say that these are independent dimers. Only then I can say that it's a perfect dimer singlet phase. And in ferromagnetic regime, you know that all the spins are going to be in the same direction. Okay, so for our convenience, because we are considering the Jx and Jy are ferromagnetic in nature, so I'll take redefine the Hamiltonian. I'll take the minus sign out, and I'll redefine the Hamiltonian like this, so that now our values of Jx and Jy are always positive. Okay. So here is the quantum phase diagram calculated from the DMRG. And here again, you see that all 6 phases are there. You have the stripe pi 0 phase, and then stripe 0 pi phase. You have 2 types of spiral phases, the perfect dimer phase here, and then the ferromagnetic regime. What is missing here is the dimer singlet phase. The reason why I have not put the singlet dimer phase here, because no matter how small values of Jx you put, immediately you see that there is a correlation function along other directions are non-zero. And in that case, you cannot write your ground state wave function as just product of dimers. That's why we think that there is a no perfect dimer phase in this regime, which is predicted by the mean field. Okay, and then what you see here is the stripe phase pi 0 and 0 pi are symmetric about the perfect dimer line, whereas the perfect dimer line also separates this XY and X spiral and Y spiral. And this we also find similar to the mean field that at the ferromagnetic case, ferromagnetic state gets stabilized only for the large Jx and Jy limit, and the X spiral is sandwiched between the stripe and the ferromagnet. Stripe pi0 and the ferromagnet, whereas the Y spiral is sandwiched between the stripe 0 pi and the ferromagnet. Okay, so now you'll ask me, how did you find that phase boundary? So we have applied two criteria. One is the ground state like behavior, ground state energy behavior, and second is the correlation. So here I am showing you the per site energy energy as a function of Jx for fixed value. The variation is along with the Jy, whereas the Jx is fixed. And this is calculated for 12x4 lattice size. And what you find is, as you keep decreasing Jx, you find that initially in ferromagnetic regime, when you come to this X spiral, immediately you see this change in the slope. And so if you take the derivative, there is some kind of kink here. Okay, and this kink is exactly at the phase boundary. Second thing, what you should be seeing is, as you keep decreasing, you find there's a maxima. And then this maxima is close to the perfect dimer, like a dimer place where there's a boundary of Y spiral and X spiral. Although there is a small deviation, this deviation is because of the finite size effect. As you keep increasing the width, because your width is still, we are considering four leg, 8 leg, and that kind of things. So as you keep increasing your width, what you find is this deviation decreases, and we expect that in infinite system, it should be exactly at the same perfect dimer line. Unfortunately, this boundary, the stripe and Y spiral boundary, cannot be detected by using the ground state energy. Okay, so let's go to the correlation. How much time I have, Rajdeep?
Yeah, you have maybe about 5 minutes.
Okay, 4 minutes. Yeah. Okay, that's great. So I think I'm on time then. Okay, thank you very much. Okay, so here I'm showing you the correlation function as a function of distance. Before I go to the correlation function, how you should see these distance r. Here is the reference point. 0 represents a reference point, and this numbering along x-axis represents your distance, whereas this numbering shows the distance along the y-axis. And what I'm showing you the correlation function for fixed value of Jx. So I'm going to cut along the Jy axis of the parameter. And for Jx is equal to 0.6, the correlation is shown for different values of Jy on 12x8 lattice. And what I want you to focus is that you see that this black curve in both the things. You see here for Jy is equal to 0, this correlation is along the x direction, and you see that it decays exponentially, and it's all ferromagnetic. Okay, and here along y-axis it is anti-ferromagnetic in nature, as is oscillate positive negative. Whereas for large value of Jy, what you find is that this color, and what you find is this is ferromagnetic. The y, along the y direction, it is ferromagnetic, whereas along the x direction it is oscillating. That means it's anti-ferromagnetic. That means you are in stripe phase pi 0, and earlier one for 0.3 you was in the stipe phase 0 pi. Okay, and the green curve is for jy is equal to 0.6, which is exactly at the dimer line. And you see that your correlation is exactly 0 in both direction. And basically, if you try to see along the diagonal direction, your values is the correlation is going to be exactly singlet dimer, and your correlation should be 0.75, minus 0.75. Okay. And as I said, that all the correlation we find is exponential decay. So now the non-collinear and the pitch angle, as you see that in X and Y spiral, you have non-collinear behavior. Here we are showing you the correlation function for Jx equal to 0.7 for 3 different values of Jy. Again, this is on 12x4 lattice system. And you see that there is a non-collinear behavior. And this spiral is along the x direction. And in fact, you can fit this correlation by using this equation. And from there, you can calculate the pitch angle. And the second figure, B figure, I'm showing you the pitch angle. And you see it's sharply going from 0 to pi. And the lower one, this curve, is a classical calculation, which predicts the classical calculation predicts you almost a flat value. So, and I have not shown you the Y direction, Y spiral direction. It's exactly similar. Only thing it switches from JX to JY. Okay, and with this, I'll put the summary here. So what I try to show you that this Shastry-Sutherland model with ferromagnetic coupling have a plethora of quantum phases. For most of the parameter regime, the correlation exhibits very short range order. And DMRG also predicts the non-collinear spin arrangement of X type and Y type spiral phases. Mean field gives you some of these phases, but their phase boundaries are almost completely wrong. And the low JX, JY parameter still requires further study to explore the new phases. With that, I thank all of you.
Thank you, Manoranjan, for a very nice talk. Questions from the audience?
Yeah, Mayuk, please.
Okay, it was really,
Mayuk, go ahead.
Yeah, it was really a good talk, Professor Kumar. Yeah, so I was just curious, is it possible from theory to know that whether, so you have different phases, so whether whether the change of the phase from one state to the other is of second order or first order?
Yeah, sure. I mean, see, do you remember the energy curve? I was showing that there is a kink. Generally, when there is a kink, there is a change of sudden change. Okay, so that's the first order. But where the peak, if you see the peak, the other one where there's a peak and flat regime, generally your phases goes, very smoothly changes, and generally those are second order transitions.
Okay. Yeah, right. Thank you very much. Yes.
You are welcome. Thank you.
Manoranjan, I have a question.
Yes, sir.
Yeah, go ahead, Vikram.
Yeah, so Manoranjan, tell me, is there any easy way to understand why, say, for example, if you do the exact diagonalization calculations, you don't see any spiral phase, but if you do a mean field, you see it, and mean field is supposed to be less reliable than an exact calculation. But the DMRG also shows spiral phases. So what's wrong?
Yeah, actually, yeah, very nice question. Here, what you find here is because this is two-dimensional, right? So if you take this thing, you'll be able to get only 4x6, or that's the maximum you can do. And what you see here, although these are short range correlations, And if they're not very particularly checking that, it looked like there is a very small hump, and then you have to fit it very properly. Even in exact diagnostic, they should have got this result, but somehow they have not. Because we get the similar nature in the exact and DMRG both, even in exact, if we can do 30 and we can get that.
Thank you.
Yeah, you're welcome.
Any other questions? We have about a minute or two. There are any other questions? Okay. There seems to be no other questions. So then thank you, Manoranjan, for this very nice talk. So maybe you can unshare and we can go to the next talk. Madhumita, can you share your screen? Yeah, so the next talk will be given by Madhumita Saha of IISER Pune, and she'll be telling us about sub-diffusive phases in open, clean, long-range systems. Go ahead.
So thank you very much for allowing me to present my work here. So this work has been recently published in PRL, and this work has been done with Archak. He's a postdoc in Trinity College Dublin, and my postdoc mentor Brijesh from IISER Pune. So first, let's look at the brief introduction of the classification of the transport. So if we have a normal metal with well-defined conductivity sigma, cross-sectional area A, and system size N, we can write down a relation between this conductance and conductivity like this, is equal to sigma A by N. Now,
Madhumita, sorry to interrupt.
Just 1 second.
Your slides are not updating.
Oh.
Your slides are not moving.
So
Yeah,
could
you please
share your entire screen, not only the PDF?
Okay, okay.
Yes. Could you just try going back and forth?
Let me see.
Yes, now it's fine. Thank you. Please go ahead.
So should I start from here?
Yes, whatever you were explaining to us. Yes.
Yeah, you can start from here.
Yeah, for a normal metal with a well-defined conductivity sigma, cross-sectional area A, and system size N, the relation between conductance and conductivity can be written like this, G equal to sigma A by N. So for a normal diffusive transport, this sigma is independent of N. So in this case, this conductance actually scales as 1 by N. Now, other than the normal diffusive transport, this conductance starts to deviate from this behavior. And in that case, for the ballistic transport, this G is independent of N, and this conductivity diverges with N. And for the perfectly insulating case or no transport regime, this conductance is exponentially decaying with system size. And in that case, this conductivity is also like that. Now, for the other, different from this ballistic, diffusive, and insulating regime, this conductance follow a power law decay, and this sigma also goes as n to the power minus delta minus 1. Now, when this delta is between 0 to 1, in that case, conductance again diverging. So this is super diffusive transport. And if delta greater than 1, in that case, conductivity is actually 0 in the thermodynamic limit. So this is the sub-diffusive transport. Now, so in about the sub-diffusive transport, so for a thermodynamic limit, it gives 0 conductivity, but still it's important in a finite system, because for making a quantum device or for mesoscopic physics, finite size systems also important. And in that case, conductance of the sub-diffusive regime is exponentially larger than the perfect insulator. And this sub-diffusive regime is usually seen in the critical regions separating the localization, delocalization, transition points. So it is associated with any kind of disorder. It may be random or quasi-periodic disorder. But here in this work, we have revealed a completely different way to where we have got this sub-diffusive transport in a clean system in absence of disorder. So this is the setup we have considered. So we have this central system which has this long range hopping and the hopping string decay follows a power law decay, so 1 by m to the power alpha. And we have attached this system with two bars at the two ends, and these bars have temperature beta 1 and beta n and chemical potential mu1 and mu_n. So this is the Hamiltonian for the central system. So where we can see the long range hopping decays as 1 by m to the power alpha, and this all these operators are the Fermi creation and annihilation operator. And we have considered alpha greater than 1 regime so that the thermodynamic limit of this system is well defined. And these are the Bath Hamiltonians. So this HB1 and HBN, these are the Bath Hamiltonians, and this capital B are the Bath operators, and Baths are also Fermionic. And this is the system Bath coupling Hamiltonian. And in this work, we have always considered a zero temperature limit and no temperature bias. So in that case, this beta 1 and equal to beta n equal to infinity. And we are looking at the linear response regime with chemical potential bias. And this bias is delta mu. So in the linear response regime, this delta mu is tends to 0. And these are the Bath spectral functions. Now, in the thermodynamic limit, this the system is a clean system. We can write down the energy dispersion for the system, and this is the energy dispersion of this central isolated system. Now, putting k equal to 0 and k equal to plus minus pi, we can get the band edges of the system. So the lower band edge is minus 2 zeta alpha, where zeta alpha is the Riemann zeta function, and putting plus minus pi, we'll get the upper band edge of the isolated system. This is 2 into Dirichlet eta function. Now, our main result of the paper that if we in the regime of alpha between 1 to infinity, in that region, if we keep this mu outside the band edges of the central system, that means mu less than minus 2 zeta alpha and mu greater than 2 eta alpha. In that case, you have seen a sub-diffusive scaling of conductance, that it's here. This conductance scales as n to the power minus 2 alpha. Now, if we put this mu exactly at the band edge, then in this case, this conductance scales as n to the power minus 2. This is also sub-diffusive, but the exponents are different. Now, between these band edges, so this is as expected, we can see this ballistic behavior as it's a clean system. So now if we look at the phase diagram, now for a fixed alpha, if we change the Bath chemical potential, there occurs two sub-diffusive to ballistic phase transition as a function of this chemical potential. And this critical point of the phase transition are actually the band edges of the system. And in this phase diagram, this is denoted by this red line and the blue dotted line. So this is the numerical evidence of this thing, that if we plot this conductance as a function of mu for different system size for fixed alpha 1.75, we can see that these vertical lines are the band edges of the system. So between the band edges, we can see there's overlap between all system size. So this is the ballistic scaling of conductance, and outside the band edges, you can see here from this plot, there is some system size scaling. Now, if we scale it with n to the power 2 alpha like this, we can see the outside the band edges, everything is overlapping, and so that means outside the band edge, this conductance scales as n to the power minus 2 alpha. In figure C, we have plotted all these conductance with system size scaling in different regions, so to ensure the phase diagram. And as a spectral function, we have chosen the Baths as a 1D semi-infinite tight binding chain. And we have calculated the conductance using the non-equilibrium Green's function technique So this conductance is nothing but the non-equilibrium steady state current by delta mu, where delta mu tends to 0. And non-equilibrium steady state current we can get from the Landau formula, where this T omega is the transmission probability. And this T omega involves the non-equilibrium Green's functions 1nth element here. And now if we plug everything in the G mu expression, so we can see this conductance in the linear, the conductance is also proportional to this non-equilibrium Green's functions 1nth element mod square. So now to understand this result more clearly, here we have plotted for alpha equal to 1.8 in this point outside the band edges, we have plotted 3 different quantities. The first, this mod G1n mu, this is the non-equilibrium Green's function, retarded Green's function, and this is small G1n, this is the numerically exact bare retarded Green's function. And we have plotted another quantity, this is the curly G1n, so this we have defined like this. And and we can see this, all these 3 quantities are showing the same scaling with system sizes 1 by n to the power 2 alpha. Now exactly sitting at the band edges, if we have calculated these 2 quantities and these 2 quantities show the similar 1 by n square scaling, but this curly G, this doesn't capture this 1 by n square scaling sitting at the band edges. So outside the band edges, so from the numerical plot, it's clear that all these 3 things are proportional, so they have same system size scaling. Now this term involves a dispersion, involves the dispersion relation epsilon k alpha. Now this long range hopping model have a special property that this long range hopping, this central isolation system in thermodynamic limit, this energy dispersion is actually non-analytic at k equal to 0. It means for any alpha, if we look at the pH derivative at k tends to 0 limit, this derivative at higher order derivatives will diverge where this integer p greater than alpha minus 1. So we have also made an non-analytic series expansion of this dispersion, and this you can see from the red line. So this dispersion in the k tends to 0 region. So here this dispersion relation involves the mod k term that ensures the non-analyticity at k equal to 0. Now, due to this non-analyticity at k equal to 0, if we want to calculate this term, this curly G term outside the band edge, we can see that because of this non-analyticity, because there will be in the contour integration, there will be a branch, and from that branch, the major contribution will come from that branch as 1 by n to the power alpha. And because this is the take-home message that the non-analyticity of the dispersion at k tends to 0 can gives rise this kind of sub-diffusive behavior outside the band. Now, as we have seen the previous slide, that the scaling with system size of the non-equilibrium Green's function is same with the bare Green's function. It is also clear that this scaling will not depend on the system but coupling strength also. So here we have plotted this Green's function for different system bath coupling, and we can see that the scalings will always be there. The same scaling will be always there. But even if we can see the scaling with the weak coupling also, but these baths are important to have these phases, because if from the isolated system conductivity or conductance, if we calculate in this region mu outside the band edge, then there will be no particle in the system, or system will be completely full. So for both the cases, from the isolated system conductivity will show no transport in these cases. And we have also shown that we have also plotted that particle density with this mu, and we can see that outside the lower bandage, this particle density, this is at number of particles actually scales as 1 by n, and above the upper bandage, we have plotted this number of holes that also is sub-extensive. So in the thermodynamic limit, this particle density is actually 0 for these phases. So it's a very small number of particles responsible for these sub-diffusive phases outside the bandages. So in these phases, so if we switch on any number conserving many-body interaction term also, that will have negligible effect in this region. So we can say, so these phases, these sub-diffusive phases are actually robust against many-body interactions also. So in this sense, this for if we look at this zero temperature two terminal harmonics transport with harmonics. Yeah.
Just that you have maybe 2 minutes to wrap up.
Yeah, sure. Yeah. So here you can see this outside the band, this conductance scaling is universal in the sense this is robust against many-body interaction and system-both coupling and this thing. And exactly at the bandage, this conductance scaling is n to the power -2. So this is also independent of alpha. So this is also true for nearest neighbor model also. So this is super universal. And for getting the sub-diffusive phases outside the bandages, so one of the intuitive picture we have given that for the long-range hopping system, it can happen that the sub-extensive number of particles can enter to the central system from the bath and can give a long-range hop and can directly go to the drain. So because of this long-range hopping, it is possible to get this n to the power minus alpha square. So that's why we can see the conductive scalings as n to the power -2 alpha outside the bandages. But at the exactly at the bandages, this n to the power -2, this for this scaling we do not have any intuitive picture. So and in the ballistic transport regime, so here there's a finite density for the particles. So in that case, obviously many-body interaction can affect the transport. So this is a non-universal behavior. So here, this is the conclusion that this is a new type of dissipative phase transition, because in an usual dissipative phase transition, what will happen? We can see a non-analytic change in the steady state of the system. And in that case, we change the parameter of system Hamiltonian or the system bath coupling. But here in our case, we can see a non-analytic change in non-equilibrium steady state when we are changing the bath parameters, not any system parameters. And this happens in the large system size limit. And this sub-diffusive phase is immune to any bath spectral function. So it doesn't depend on which bath spectral function we have taken. And this is also independent of the system bath coupling. And this is strictly a quantum phase transition because it's strictly at 0 temperature. At finite temperature, we'll see crossover from the sub-diffusive behavior to ballistic behavior. So these are the further works in this direction. We can think that, yeah.
Madhumita, you have to wrap up.
Yeah.
Just okay. So questions from people in the audience? So one question from me, Madhumita. You took this bath with a parabolic density of states, right? Some sort of a parabolic.
So one day.
The bath it was always kept much larger than your system.
Yes.
System. So lambda was how large compared to, let's say, your zeta alpha?
So if you guys, so we have considered a one-day semi-infinite tide winding. So I have considered this T naught as something 8 something, so that 2 not, so bath bandwidth is something large, is something minus 16 to 16, this kind of, and minus 2 zeta alpha is compared.
So you are always in some middle part, you accessing essentially the flat part of the bath bandwidth. Okay, okay. Okay, and any other questions? If not, let's thank Madhumita for a very nice talk. And Madhumita, can you stop sharing so that we can move on to the next talk?
Sure.
So, Sahana, can you share? Right. So the next talk would be given by Sahana Das from IIT Kharagpur, and she'll be talking to us about ground state wave function for 2/5 quantum Hall state from the gapless Gaffnian wave function. Yeah, can you share your slide? Yes, go ahead.
Sahana, we are unable to hear you if you're speaking.
Are you speaking? Maybe you also want to use your mic. Yeah.
Can you try speaking?
Can you speak just so that we can see?
Try to check if your audio input is there in the proper place. No, not that. In the microphone settings on the left, the little icon that you have.
Okay. Am I audible right now?
Yes. Thank you. Please go ahead.
Yeah.
Okay. Thank you.
Okay, go ahead.
Okay. Okay. So in today's talk, I'm going to present the ground state wave function for 2/5 quantum Hall state, starting from a well-known wave function, which is known as the Gaffnian wave function, and this wave function describes a gapless quantum critical state. Now, after a very short introduction, I will describe the background behind the our proposed wave function for this 2/5 state, and I will describe some numerical results to validate our wave function. So this is very common experimental figure for the resistivity as a function of a magnetic field, which provides the fractional quantization or integer quantization of Hall effect. Now, for any two-dimensional electron gas present in a very strong magnetic field and low temperature, the conductivity, Hall conductivity, as well as the resistivity becomes quantized with a quantum number nu, where nu is the fading factor, and this quantum number can take the value integer as well as the fraction. Now, in this our work, I will consider only this 2/5 quantum Hall state. Now, before going to the main work, I want to describe some basic physics behind the fractional quantum Hall effect. Now, for a two-dimensional electron gas with strong perpendicular magnetic field, the many-body Hamiltonian will take this type of form, and the energy level of this Hamiltonian becomes quantized, and we know this energy levels as Landau level. Now, for single particle wave function in this lowest Landau level, we can say this. We can write this type of analytical wave function, where Z is the particle coordinate and LV is the magnetic length. Now, for any system with total flux quanta n phi, this m can take any value from 0 to n phi. So this m is basically the degeneracy of any Landau level. Now, for a fully filled Landau level with n particles with this type of Hamiltonian, the many body wave function of this Hamiltonian can be written by this type of simple trivial wave function. Now, if we consider the partially filled Landau level, then we observe fractional quantum Hall effect. Now, for partially filled Landau level, the system becomes strongly correlated. Now, this huge degeneracy is lifted by this Coulomb term, Coulomb interaction. Now, this total Hamiltonian is now not exactly solvable. This is the reason here for this fractional quantum Hall effect, there exist many model wave function to describe this effect. Here we have also another term, Zeeman term, but for strong magnetic field, we can neglect this term. Now, I have already mentioned that for fractional quantum Hall effect, we have different model wave function to describe the state. So we start with the composite Fermionic wave function, which is known as the best fitted wave function for any state in the lowest Landau level. Now, the composite fermion is basically one type of quasi-particle which consists of electron attached with even number of flux quanta. Now, here for this 2/5 state, each electron is attached with 2 flux quanta to become the composite fermion. Now, due to this flux attachment, the effective flux is reduced. So we have to consider mean field approximation. Now, the composite Fermionic wave function for this 2/5 state can be written by this type of wave function. Here, this product term, this factor is basically due to the flux attachment, 2 flux attachment with each particle. Now, this phi 2 is basically the wave function for composite fermions which fill 2 effective Landau levels. This PLL is the projection operator which projects the whole wave function into the lowest Landau level. Now, due to this projection operator, the whole wave function becomes a little bit complicated to write down in a complete analytical notation. However, this wave function provides very well description for this 2/5 state, and it satisfies all the experimental results very well. So we can say that this composite Fermionic wave function is a nice description for this state. However, there are some states like 5/2 state which cannot be simply described by this composite Fermionic wave function. So Moore and Reed proposed another wave function for this 5/2 state, which comes from a different approach known as the conformal field theory approach. Using the same approach of this Moore-Reed wave function, Simon and his collaborators proposed another wave function for this 2/5 state, which they named as Gaffnian wave function. This Gaffnian wave function is actually an exact zero energy ground state of a 3-body model Hamiltonian. Now, this wave function has a very high overlap with the exact Coulomb ground state. However, the CFT used for this Gaffnian wave function is non-unitary, and theory says that any non-unitary CFT provides gapless state. So, where our fractional quantum Hall effect gives us a gapped state. So, this wave function cannot describe a true fractional quantum Hall phase. Rather, it provides a quantum critical state. Now we are again in the limit of composite Fermionic wave function. I have already mentioned that due to the projection operator, the whole wave function becomes a little bit complicated to write down. But in 2018, S.S. Mondal has proposed a generalized form of composite Fermionic wave function taking the projection operator. Now, after this projection, this wave function for 2/5 state can be written by this type of a complete analytical notation in the relative coordinate Uij Zi minus Zj. Now, taking this in mind, we represent the Gaffnian wave function in a new way, in a very similar way, representing it as a paired state of different flavored composite fermions. Here, this is a pictorial representation of this Gaffnian wave function. Here Uij square is basically the two flux attachment with each particle to become to make it composite fermion. Now these two multiplicative term gives this preserves the fermionic representation of these two different type of composite fermions. Now this last term is basically the pairing term, which gives the pairing between two different color flavored composite fermions. Now from these two wave functions, we see that these two wave functions are very much similar. Only the difference is in the last term. Now this term is basically a part of this term. So we can again say that this Gaffnian wave function is a part of the composite fermionic wave function. But the rest of the composite fermionic wave function, rest part, is very difficult to understand. So we need another new wave function so that the new wave function along with the Gaffnian wave function can describe this 2/5 state, this gapped 2/5 state. So taking the new representation of this Gaffnian wave function, we slightly modify this picture by changing the flux attachment between any two pairs. Now here for these two pairs, we have attached two upward flux in the same pair and two downward flux quanta between similar color flavored composite fermions, so that the total flux of any particle remains the same. Here only one particle can see only one colored flux, only colored flux of another only when if the colored flux of their flux matches. So for this particle can see the flux of this red particle with orange flux, two upward flux, and for this particle with two pink downward flux. From this representation, pictorial representation, we can write down a new wave function, and we named as modified Gaffnian wave function, where these flux attachment terms are taken care by this last term. Now, taking these two wave functions, we'll finally propose a final wave function, hybrid wave function, taking the linear superposition of these two wave functions with respect to their normalized form and a suitable linear coefficients. Now we have to validate our wave function, so we have calculated some numerical results. So this table is giving the overlap data of different wave functions with the exact Coulomb ground state. Now we have calculated all the data for different particle system. Here from this table, we see that the overlap of Gaffnian wave function as well as the modified Gaffnian wave function with the exact state is somehow high. But if we take the linear combination of these two wave functions, then we see that the overlap is very much increased and it is very similar to the composite fermionic wave function. Again, if we calculate the energy of these the different wave functions, we see that the energy of our hybrid wave function as well as the composite fermionic wave function is very much close to the exact Coulomb energy. Sorry.
Just one thing, you would have to probably wrap up in maybe a minute or minute so.
Okay,
yeah?
okay, yes, okay. Yes, definitely. Okay. Where the energy of the Gaffnian wave function is slightly higher. Here we have considered the linear superposition of Gaffnian and modified Gaffnian wave function. So we have to check the values of the linear coefficients in the thermodynamic limit, that is when n tends to infinity. So we have plotted the coefficients with respect to the inverse of the particle number. And from the quadratic fitting, we see that this ratio is giving us a positive value in the thermodynamic limit. So this confirms that along with the Gaffnian wave function, our modified Gaffnian wave function is also important to describe this 2/5 state. Here we have considered a model Hamiltonian taking a three-body model potential for which Gaffnian wave function is exact and a two-body exact realistic Coulomb potential. Here, when alpha equal to 0, we are in the gapped Coulomb limit, and when alpha equals to 1, we are in the gapless Gaffnian limit. Now we have taken the overlap of different wave functions with this model Hamiltonian, and we see that the overlap of Gaffnian and modified Gaffnian wave function decreases if we decrease the value of alpha. But if we take the linear combination, then the overlap of our hybrid wave function as well as the Gaffnian wave function increases, and it takes a maximum value near the alpha is equal to 0 point, that is near Coulomb point. So these figures are for different particle system, and from all these figures we see that our hybrid wave function is very much accurate for near the Coulomb point, that is the Coulomb point where the state is itself gapped state. So our wave function is very much accurate for gapped phase. Finally, I want to conclude with some interesting points. So for the first time, we have constructed the Gaffnian wave function, considering it as a paired state of interflavored composite fermions. And we have modified this state by taking a minimal modification of this state. And the linear superposition of these two wave function can provide the state, can describe the 2x5 state. Our hybridized state is basically the very accurate for the Coulomb potential, near the two-body Coulomb potential, where the state is itself gapped. The most interesting point is that the quasi-particle of composite fermion wave function for 2/5 state gives abelian statistics, but our hybrid wave function will provide non-abelian quasi-particle statistics, because it is the paired state of composite fermions with dissimilar flavor. So this will be very interesting to see under what condition the abelian phase of composite fermion or the non-abelian phase of our hybrid state will occur. Again, we see that
Sahana,
the energies of these two.
You would have to.
Just one.
Yeah, sure. Just finish up.
Okay, so and due to the same energy, there is a spontaneous position of these two topological orders based on the external condition. So I want to acknowledge these collaborators. Thank you.
Okay. Thank you, Sahana. Is there any question from the audience? I guess the audience is hungry. And anyway, we are kind of over time already. So let me thank Sahana, and let me thank all the